We're rolling.
Okay, it's part 2. We saw last class, and also on the homework, that whenever there are natural logs involved in your derivatives, it makes it really easy to break them up. So let's just suppose someone gave me the following function. Okay, this looks terrible. Here's why it's so terrible. Because, first off, I need to use the quotient rule. Inside the quotient rule, I'm going to have to use the product rule. Inside the product rule, I'm going to have to use the chain rule. And I'm also going to have to change the chain rule. This looks like a nightmare. This is just a terrible, recursively difficult problem, which, though definitely doable, just kind of sucks. So, what can we do? We can use the power of logarithms to simplify, to help us simplify this. So here's this bold and wild move. The bold and wild move is just take the natural log of both sides. So if I take the natural log of the left side, of course I get ln y. If I and now here I'll just write this. This is x cubed root x squared minus 4 over sine 4th x. Okay, now I use the power of the natural logarithm to just like decompose this, right? What's up?
Why do you use natural log and not a log with a different base?
Oh, I use natural log because its derivative is simple. It's just 1 over x. If I use a different base, then I have these disgusting extra 1 over ln a factors. So this is going to just be awesome, right? Because, okay, I'll skip some steps because whatever, we're all experts here. The natural log of like a over b, well, maybe I won't skip steps. So it's like, this is like ln of x cubed times x squared minus 4 minus the ln of sine to the 4th x. Can I simplify this more? Of course I can. Because now again, this is just ln x cubed plus ln root x squared minus 4. And then since that 4 is really up there, this becomes minus 4 ln sine x. And then here, of course, as you're all seeing, this can also be simplified. So we get 3 ln x plus 1/2 ln x squared minus 4 minus 4 ln sine x. Notice, I have not taken the derivative yet. All I've done is just perform this kind of optional algebraic move. But now, if I'm going to take the derivative of this, it's going to be really easy to do, because taking the derivative of pieces is always easy, and you don't get this kind of computationally recursive, kind of annoying work to do over there. Okay, so now let's take the derivative. Okay, so, and note, I have to take the derivative of both sides with respect to x, because that's kind of my goal. Now, what is the derivative with respect to x of ln y? Well, this is something we kind of talked about last class. So you should be thinking, all right, what is the derivative of ln y? Well, the derivative of ln y is 1 over y back inside for the derivative of y. And since we're differentiating with respect to x, the derivative of y is just dy dx. And now we can differentiate the right-hand side. Well, now this is really easy, right? This is 3 over x plus 1/2, and then 1 over x squared minus 4, back inside 2x, minus 4, the derivative of ln of something is 1 over the something, back inside for the derivative of the something. Okay, this, my experience teaching, is that this kind of bothers some people. So let's just maybe even take another moment and think about what's really going on here. What's really going on here is I have some function that I want to differentiate. Let's call this function u. So y is like some function of x. And what I'm basically doing is I'm saying, okay, so given that that's in the background, then the question is, what is the derivative with respect to x of y? Well, the derivative with respect to x, that's not what I meant. I do this, and then I take the natural log of both sides. So I get ln y equals ln of u of x. And now I want to differentiate this side. So what is the derivative with respect to x of ln y, well, the derivative with respect to x of ln y, again, it's like a chain rule situation, right? How does ln y respond to a small change in x? Well, this is, if this explanation doesn't bother you at all, then great. But if you're feeling a little uneasy about this, of course, since ln y is just ln of u of x, you could rewrite this as the derivative of ln of u of x. And that, what is the derivative of ln of something? Well, it's 1 over the something back inside for the derivative of the something. And so this is my final answer, but that's exactly what I get here, right? Because 1 over u of x is just 1 over y, and u prime of x is just dy dx. So I don't know if that was convincing at all. So anyway, what's so awesome about this is now what is dy dx? That was my goal, after all, was to figure out what dy dx was. Well, now I multiply both sides by y. What's y? Well, it's that. And so I end up with x cubed root x squared minus 4 over sine to the 4th x, and then times all this stuff. So 3 over x, plus the 2's cancel, minus 4 cotan. And that disgusting mess is the derivative of this function, but it really didn't take that long relative to doing it out the long way. Giles, any comments? Okay, Giles is good. All right, this has a name. This is called logarithmic differentiation. In logarithmic differentiation.
Can I now add one comment?
Yes.
Any reason you didn't just at the start say dividing by sine is the same thing as multiplying by cosecant?
Oh yeah, I could have just rewritten this as cosecant to the 4th. It still is a big product rule, so that doesn't suddenly make the problem easier. But logarithmic differentiation does make the problem significantly easier. And well, basically logarithmic differentiation says if I'm taking the derivative of some really complicated thing, let me just, because I feel like it, take the natural log of both sides. And the natural log will split up these things into much smaller things. I think of this like a bug. This is like, you ever see those videos, those like nature videos of like ants and flies and stuff that like barf on their food to digest it? That's exactly what's going on here, right? The natural log is like insect barf. It like you let it loose on some big complicated thing and then it decomposes it into very simple tiny bite-sized pieces which can then be differentiated really easily. Or if you're okay, good. That was disgusting. So that's what logarithmic differentiation is. And it depends on your ability to take the derivative of expressions like ln y and to realize what's going on. Alright, so that is logarithmic differentiation. This is what I like to call logarithmic differentiation optional. But there is also another category of problems called logarithmic differentiation obligatory. These problems, this is, in fact, your entire life has been building up to this point. You have never before encountered this just like magically awesome and crazy, ridiculously cool function. And before, probably. And you're probably thinking, oh man, x to the x. Now things are getting really serious. I've never seen him before. That's because without calculus, there's barely anything we can say about this function. So let's, but now with calculus we can. All right, so how do we take the derivative of this? Well, first of all, we have to note that this is not an exponential function. So here's an example of a terrible, terrible thing to do. This is not, I do know how to take the derivative of things of the form a to the x. We learned that last class. It's just ln a times a to the x. But this is not one of these. Okay, so this is a completely different category of problem. So this rule not applicable. It is not an exponential function. Another rule that's not applicable is the power rule, right? So this is not a function of the form x to the n. Sure, the derivative of that is just nx to the n minus 1, bless you. But this is not one of those either. This is neither a power function nor an exponential function. It's just some other awesome, crazy thing. So no previous rule I have is going to apply. I need to do something wildly new. Okay, what do I do? Well, somehow this x up here in the exponent, like, just, it can't be there. I need to get it down. I need to I call that rescue the princess. We need to rescue the princess. When you have variables up in high towers, you have to rescue the princess, and you do that with logarithms. So this is an example of where we would use logarithmic differentiation. I take the natural log of both sides, I take the natural log of the left, and I take the natural log of the right, prior to differentiating. No calculus has happened yet. And then ln of x to the x is just x ln x. And now this is something I do know how to differentiate. Now I take the derivative of both sides. So the derivative with respect to x of ln y, and I take the derivative with respect to x of x ln x. The derivative with respect to x of ln y is 1 over y, back inside, dy dx, which was, after all, the thing that I wanted to begin with, was dy dx. And the derivative of x ln x, well, now I have to use the product rule. So derivative of the first, 1 times the second, plus the first times the derivative of the second. And so what I get is that dy dx is simply y, which is x to the x, times ln x plus 1. That is, in fact, the derivative of this function. And there's really no other way to do it. Okay, hopefully that makes sense. Let's do a harder one. Y equals x to the cosine x. Okay, if you were all in class here, I would now give you like 3 minutes to do this problem. So please hit pause on your whatever playing device and just like do this problem using this previous examples as your inspiration, and then try it for 2 minutes, actually like really try it, and then check back in and see if you got it right. Okay, now I'm going to do it. So, I take the natural log of both sides. I take the natural log of both sides simply so that I can rescue the princess up here. So this is cosine x ln x. This is ultimately just like the previous problem. Now I differentiate both sides. The derivative of ln y is 1 over y dy dx. And the derivative of cosine x ln x as well. Derivative of the first, negative sign, times the second, plus the first times the derivative of the second. So this thing is not particularly beautiful or anything, but I get that dy dx is x to the cosine x times, because that's what y is, times all of this. So I guess cosine x over x minus sine x ln x. And I could get a common denominator if I wanted to, but I don't think it. Okay, that is logarithmic differentiation. Man, there's still a lot more to do. All right. So let's talk about something. Let's go to that board. So if you understand these concepts, then you're ready to do some serious implicit differentiation. Now, what is implicit differentiation? We've kind of been doing it already. It is basically an application of the chain rule, but in a kind of a different context. So, all right, up to this point, we've been very sort of formal with everything. I've given you functions and I've asked you for their derivatives. But now, suddenly, I'm not going to give you functions anymore. I'm going to give you relations. So take x squared plus y squared equals 25. Okay, I picked this example because this is just a circle. So the fact that this is a circle means I can like talk about this pretty intelligently, and I know what this, what points satisfy this relation. It's all the points on a circle of radius 5. So this is definitely not a function. I'll even just write that. You know, y is not a function of x. But even though y is not a function of x, that doesn't mean that I don't have interesting questions to ask about this function. For example, one question. Well, okay. So first of all, even though y is not a function of x, this is a relation, but this relation implicitly defines two other functions. So this is y is not a function, y is a relation, but this relation implicitly defines two other functions. Implicitly defines two other functions. And the two other functions are, well, they're the functions that you would probably use if you were trying to graph this circle on your calculator. If you solve for y, you get that y is root 25 minus x squared, and that y is also negative root 25 minus x squared. So in implicit differentiation, what you're essentially doing is you're treating a relationship between two variables where even though one is not a function of the other, if you wanted to, sort of maybe sometimes, you could express one of the variables as a function of the other, or as multiple functions of the other. But actually, you don't have to do any of that. All right, so here's what I want. My goal here, what I want, is dy dx. This is sort of awkward to do without an audience, but what is dy dx? What does dy dx actually mean? Well, of course, in some ways, it's just shorthand for the derivative. But in other ways, it's really saying something deeper about the relationship between the x and y variables. Dy dx is the rate of change of y with respect to x. In other words, dy dx is giving us, as x changes by a tiny bit, by how much does y change? So what does this actually mean? Well, it means just the slope. Take some point, take the point, picture not exactly to scale, take this point 4, 3. Dy dx at the point 4, 3, what does that mean? Well, that's basically saying, all right, when x is basically 3 and y is basically 4, if I'm there, if x is, what happened? Oh, did I say it wrong?
Yeah, flip them.
If x is 4 and y is 3, then for a small change in x, how much does y change? In other words, if I increase x by some infinitesimal amount, by what infinitesimal amount does y increase by? But if you think about what that's saying, that's just the slope. Terrible line. But that's just what the slope, that's what the slope of the line tangent to the curve is actually telling you. It's telling you, at that moment, if x gets a little bit bigger, what happens to y? And in this case, if x gets a little bit bigger, y is going to go down by a little bit. How much? Well, this is actually a pre-calculus problem which we can just solve. Because this line, so if I draw this line, that is perpendicular. And this is 4 and this is 3. Doesn't totally look like it on my picture. If that's 4 and that's 3, then the slope of this radius is rise 3, run 4. So that's just 3/4. So if the slope of that radius is 3/4, then by algebra 1, the slope of the blue line must be the negative reciprocal. It must be negative 4/3. Okay, so I already think that the answer to this question is negative 4/3. That the slope of the tangent line to this curve is going to be negative 4/3. All right, what does calculus tell me? How much time do I have left in this video?
10 minutes.
Oh, perfect. What does calculus tell me? Well, let's take the derivative of both sides. And we're going to take the derivative of both sides with respect to x. So this assumes that you are like kind of experts on or that you're comfortable at least with implicit differentiation. So, what is the derivative with respect to x of x squared plus y squared? Well, let's just, maybe I'll be even more particular about this. Of course, the derivative of a sum is just the sum of the derivatives. So really this is two separate problems. So what is the derivative with respect to x of x squared? Of course, that's just 2x. The derivative with respect to x of y squared, okay, well now it's kind of tricky, right? Y is a function of x. Or rather, we should say that y implicitly defines two functions of x. But if y depends on x, I want to know, how does y squared change as x changes? Well, again, it's just another chain rule situation, right? The derivative of something squared is 2 something back inside for the derivative of the something. That's the key step. And then the derivative with respect to x of 25 is just 0. Okay, well, if my goal is to figure out what dy dx is, then I'm almost there, right? I get 2y, dy dx, I just subtract 2x from both sides, and then I just divide by 2y. So I get dy dx is negative x over y. Okay, that's a very strange formula because I have x's and y's mixed in. But that's exactly the kind of formula I want. What is this formula? This is essentially a formula which will tell me for a given ordered pair x comma y what the slope of the tangent line to the curve is at that point. So how is this used? This is used to solve problems like the one we have, right? What is dy dx at, for example, the point 4, 3? That's saying, all right, what is the slope of the tangent line when x is 4 and y is 3? Well, the formula says it's just negative the x-coordinate over the y-coordinate, which is exactly what we got up here. And I could plug other numbers into this formula. For example, what's dy dx when x is, I don't know, what's another good one? How about negative 4, 3? That would be asking for like that slope when x is negative 4, 3. Picture not so great. Well, according to the formula, it's the opposite of the x-coordinate, in other words 4, over the y-coordinate 3. So that tells me the slope of that green line is 4/3. Okay, so we've achieved exactly what we wanted, which is to say that when x is negative 4 and y is 3, a small change in x will induce y to change by around 4/3 of that x. Okay, last thing on this subject, let's see. We can also take the derivative again. All right, so I want to take the derivative with respect to x of dy dx. And what question is that going to answer? That's going to tell me the rate of change of dy dx with respect to x. In other words, that's going to tell me if x changes by a little bit, by how much does the slope of the tangent line change? Okay, how do we do this? Well, first of all, you have to get comfortable with this annoying notation that people have. So this is what we're doing, is taking the derivative with respect to x of dy dx. Well, people have looked at this in the past and they've seen a d and another d. So there's this unfortunate notation, which is people just write this as d squared y. And people write this as dx squared. Okay, do not stress over this or look for a hidden deep meaning. There's no reason why this is this. It just is. Okay, Giles, you have anything to say about that?
No.
Good. Okay, so what is d squared y dx squared for this particular problem? Well, it's just the derivative with respect to x of dy dx. In other words, it's the derivative with respect to x of negative x over y. Now I can just do that. That's going to require the quotient rule. So let's do it. So this is going to be the derivative of the top, which is negative 1, times the bottom, plus the top times the derivative of the bottom. and that would be dy dx, all over the bottom square. Okay, so what do we got here? Well, I already actually, so this is negative y plus negative x times, well, dy dx I previously calculated is negative x over y. So all of this over y squared. So if I keep simplifying this and I get a common denominator, this, did I do this right? Oh yeah. This turns out to be, I feel like I did something wrong. Oh, this should be a minus, that's why. I messed up the quotient rule. Please edit that out. Derivative of the top times the bottom minus the top times the derivative of the bottom. I'm sorry if you've been twitching for the last 30 seconds in pain. I forgot the minus sign. Okay, but now it is correct. And what do I actually end up with? Well, if I get a common denominator, I get negative y squared minus x squared all over y squared. Or this could be written as negative x squared plus y squared over y cubed. Going really fast now. Of course, x squared plus y squared is just 25. So actually, this is just negative 25 over y cubed. Okay. I went really fast because there's no one here to slow me down. No confused faces. But what I just learned is that d squared y dx squared for this particular problem is negative 25 over y cubed. What does that actually mean? It gets pretty hard to figure out what this means, but if you're willing to put a lot of mental energy into this, what this is really saying is take a particular value. Like how about here? Okay, here the y coordinate is 5. And what this is saying is that the second derivative is negative 1/5, which means that the slope is changing negatively, but not so much. So that the rate at which the slope is changing is negative, but relatively slight, which seems to be about what a circle does, right? When you're up here, the slope is changing, but the slope is not changing by much. It's changing very slowly and negatively, which is consistent with when y is 5, that number being negative 1/5. However, when y is 0, let's say when y is a tiny positive number. If y is a tiny positive number, then this is negative 25 over 0 plus. This is like negative infinity, which is basically saying that as the slope gets closer to the point 50, the rate at which the slope changes is like nearly infinite. So not only is the slope of the tangent line here negative, but it is changing really fast. Here it might be negative 10. By the time you get here, it's like negative infinity. So this, if you're really willing to stretch your brain, this does kind of mean something. It's the rate at which the slope of the tangent line changes. Okay, what's the time?
90 seconds.
Okay, perfect. Stop.